Awesome. The recording started. So Matt and James asked for the reading next week. Is there anything specifically you want to look at, or are we just exploring the website data from Viz? You're just exploring the website data from Viz. Next week, I'll be talking about kind of the underlying concepts from that website. So I want you to kind of be familiar with it, because that's going to structure the lecture, and also is going to be important for the actual assignment. So good question, Matt and James. So yeah, just get familiar with that. Okay, so today I'd like to talk to you a little bit about the thinking behind one of the software packages that you've been using a lot in this course, which is ggplot2. Okay, so we'll be talking mainly about what this GG stands for and how you can kind of think about that when you're working with your data. So to get started, it's important to recognize what Hadley means by GG, which is the grammar of graphics. And that's why it's called ggplot. And what is a grammar in this sense? Well, a grammar is a collection of formal rules for the way that objects can be combined. When we speak English, we know how to construct sentences, in part because we intuitively, generally we don't formally, know the grammar of the English language. You can hear a construction like John and me went to the store and guess that something about that sentence isn't right because the phrase, what's going on? Sorry, hold on. My pen seems to have died. That's going to be a problem. Sorry, hold on. So, let me just stop sharing. So, one of the kind of concerns or major conceptual things that this grammar of graphics component is going to try and get you to realize or engage with is that a grammar is kind of like a collection of or a system of rules that govern how different objects can relate to one another. So the reading today was this reading here, a layered grammar of graphics. And so I will be charging my pen for a little bit, and then we'll kick back into slide-based drawing, but I can do most of what I want to do by talking about this article here. So we'll do that today. The main point of a grammar of graphics is to identify the different individual components of a plot and give you a structured set of rules for how they can be combined. Right, so here, Wickham's talking a little bit about the way in which plots are constructed and the components that can be on a plot. So what you see in this breakdown of a plot on the bottom is that he's separated it into three elements. One of them on the left, Wickham calls the geometric object. A geometric object is a shape that describes the data. So the shape can describe the data based on its position, which is what's going on here, it can describe the data based on its actual geometric structure. Is it a point? Is it a line? Is it a star? Is it a bar? In this case, we've got 4 geometries, each with distinct positions, but we've also visually separated them into 2 groups. One collection of points or circles, and another one a collection of squares. So geometries, these geometric objects, are descriptors of the data. They're kind of the main mechanical thing that you use to describe your data. The concept in the middle is, if you cannot see my mouse, can you? Okay, that's all right. The concept in the middle is known as the scale. So in ggplot language, in the way that the grammar of graphics works, anything having to do with like your x-axis or your y-axis, the frequency of ticks that are made on those axes, in this language, the little markers that apply to the vertical and the horizontal axis are known as ticks. All of that stuff has to do with the scale of the graphic. In addition, something implicit that happens because of the way that this graphic is drawn, those scales provide a coordinate system. The position of every circle or every square geometry uniquely encodes some value in a coordinate system. So the circles each have a distinct value of A and a distinct value of C. Likewise, the squares have a distinct value of A and a distinct value of C. So together, the position of the geometries encodes a position in a coordinate system. And in this case, the coordinate system is just the Cartesian coordinate system, right? So there's some kind of square-based reckoning where every shape has a unique position in A and C. The rest of it, the component on the right, is known as an annotation. So an annotation is anything like a label or a plot or a title, anything that you're inserting into the plot, that kind of thing. So when you build this together, Hadley's encouraging you to think about 3 different components: the geometry, the scale, and then basically everything else. Okay? ggplot is built on top of these kinds of constructs. So going down a little bit in the reading, the main concepts are here in this table. My pen is almost charged enough to finish the lecture, so I'll be almost ready to go here. So the main point of the reading and the main structure of ggplot is this kind of data and mapping, layer, scale, coordinate, and facet. So each of these things govern different components of a plot. And each layer is a unique description of a collection of geometry or summary of the source information. So in ggplot, when you set up your initial kind of specification of the plot, you should recognize that the first part of it, the part that says ggplot2 with defaults, that is the standard ggplot call. So I've gone back to sharing the iPad screen. My pen should be working fine now. Can everybody see the iPad screen? Cool. Thanks. Okay, sorry for that. So the main point here, so Wickham has this kind of division of ggplot and by our kind of custom, we always put the data first. And then normally we do something like AES, which is a function, where we do some stuff inside of it. And all of this table in the Layered Grammar of Graphics paper is doing is showing you that this AES specification is something called a mapping. So the mapping connects the data to a scale. And that's what the AES component does. It's some way to specify that parts of my data are going to connect to parts of my plot. Okay? So one way that we've seen that before is you might say x is equal to, I don't know, variable 1, and y is equal to variable 2. And then that means that I'm going to have a scatter plot where, or not necessarily a scatter plot, but I'm going to have a plot where one of my axes, the horizontal, is going to be v1, and the vertical axis is going to be v2. So that's what the mapping is doing. And every time there's a mapping, it's going to suggest that some geometry gets drawn with that mapping. The reason why we have this kind of AES early on in the ggplot call is because that lets us specify reasonable defaults every time we want to add a geometry. Okay? So we'll break this down a little bit going forward, but I want to show you the structure from top to bottom first. So the ggplot involves that first call. And then every graphical element that you add to the ggplot usually is done using a plus. And I guess in this case, we would use the plus up here so that the line continues. But then every single geometric element is something that Hadley's calling a layer. And that layer is specified by data, a mapping, a geometry, a statistic, and a position. So let's just focus in on these three parts: the geometry, the statistic, and the position. Okay. So every layer is composed of a geometry, or is expressed inside of a geometry, I guess it's better to say. So in our example before, we had a couple of circles and a couple of boxes on a variable A and a variable C. So the geom, in this case, the geometry that's being used is a description of these elements. So what are these elements? Well, conceptually, they're points. They occupy a specific location in a given position in the coordinate system, the unique combination of values for A and C. Okay? that means that their statistic is what's called an identity. So it's an identity in this case. Why is it an identity? What the hell does that even mean? Okay. So assume that up top, this would say something like x is equal to variable a and y is equal to variable c. This would mean that each row of our tidy data frame has two components, one for A and one for C. And this would be something like A1, A2, A3, A4. And this one would be something like C1, C2, C3, C4. So the location of this very first point is going to be at A1, C1. That is just the information contained in that row. So this statistic, for most purposes, is just going to be identity when you're using geom_point. There are other kinds of statistics that can be shown implicitly with your plot. For instance, if you use a geom histogram, the statistic is generally a count. So I might have a bin that describes how many A1s fall within a value of, let's say, or how many of my observations fall within each collection of break. In a histogram, generally this statistic is a count. Sometimes it might be a frequency if you want to get the percent of observations that fall within that area. But the point is that every visualization is an implicit combination of a geometry. Is it a point? Is it a bar? Is it a hexagon? A statistic about the data that pertains to that. Is it a count of all the observations that fall in a bin? Is it a record of the location? And then it's some information about where to put that. In the case of a histogram, we just put that at the location of the bin. In the case of a scatter plot, where we have our circles and our squares, the position becomes the statistic. So we just put the point at its unique value of A and C. Now, since this article was written describing the theory about how all these components relate to one another in layer, we've kind of made this a little simpler. Nowadays, you use something like geom_point. Or geom_histogram. To do what you want. So geom_point still has a stat inside of it that it can change to give you something else. You can still do various kinds of computations and remappings and things like that. So, for instance, if I had my original plot of point and square, and I have A, and I have C, if I said something like stat is equal to x minus x mean, then I would shift all of my positions over to the average value on the x-axis. The statistic is what they call a transformation. And that can be a one-to-one kind of correspondence, like the identity, or it can be any arbitrary function. In the geom histogram, like we said, stat is usually count. So the stat is a transformation. It says take the data and convert it into something that gets put in the plot. And normally, we think of the stat as something that's intrinsic to the geometry, right? So, for instance, geom point, geom histogram, geom line, geom box plot. You've used a lot of these things. So geom point, its statistic is usually the identity. It just takes the positions that are given to it and spits them out onto the plot. The stat for a histogram is normally count. The stat for a line is also normally identity. So we normally want to make a line by taking every single point of my input data and mapping that exactly to a continuous path across which I draw a connecting line, right? So normally the stat for a line is also the identity. And box plot has a bunch of them. So it has like the median, the interquartile range, etc. But the point is, all of these geometries and the way that you represent them are conceptually connected to one of these other kinds of statistics. Okay? And next week, we'll talk a lot about what geometries do I mix with what statistics to make my point. But the main idea here is that the actual geometry, the actual shape or style of thing that I'm plotting can actually be distinct from what the statistic is. Sometimes you'll see plots that don't conform to the way that you think they should based on the statistic. And I'll give you one example of this because I saw someone else using it and I think that they copied it from me in an earlier example that I gave to you. In some kinds of plots, I might have a couple of categories. Let's say category A, category B, and category C. And I might be interested in visualizing the distribution of points. Or sorry, not distribution of points, but I might be interested in visualizing the distribution of some Y value across those groups. So this could be waiting times in a pub. Very easy, very similar to what you've seen before. If I just plot a bunch of points, I'm going to get what you call overplotting, right? So they're all going to have the value A, so they're all going to line up on top of one another, and they're going to be pulled around the distribution of Y. And then for B, I might have a different collection of points. And for C, I might have a different collection of points. Actually, yeah, that's fine. Okay? And that's because the statistic identity is just mapping the input. Is it an A, B, or C? And is it at this Y, that Y, or a different Y? It's mapping those directly to the position in the plot. But one might use something called geom B-swarm. which is a special combination of two kinds of statistics. And what a B-swarm plot looks like: same scales, same geometry, but it's going to stack the observations the best that they can close to their y value. So they're all going to be points, and you're going to be able to see every single point. But then they're going to form these kinds of like big clouds where they exist. So instead of overplotting, because they all have to occupy the same A location, something like a B swarm tries to get them as close to their Y as possible without stepping on top of one another. That's a term to describe this kind of point-based histogram. And there's a ton of these kinds of jargony terms. There's a ton of these kinds of different geometries that we use to describe a unique mapping between a geometry and a statistic. Where Wickham's coming from in the design of ggplot is that in theory, one can just do this by mixing up the statistic and geometry and picking your own kind of custom things. In practice, making this work is really hard. And this is part of the reason why ggplot, if you want to make something very simple, is very easy. But if you want to make something that's very complex, it can be very challenging to do so. There's so many different ways that these different factors can be combined that it becomes very challenging to understand their interactions. So while this is where ggplot is coming from, in practice, contemporary R focuses on defining these kinds of special combinations of points and statistics. So maybe this is something like stat is equal to count, but also kind of approximate identity, because it's trying to pick the closest point it can for the point that doesn't overlap any other points. So in R, generally, we call this kind of unique combination of a geometry, here again it's a point, but then a new statistic, we generally give that a new name. It doesn't change the fact that it's fundamentally a point with a different statistic. But changing the way that these defaults work is really the most important and flexible power of ggplot. Because it's been so abstracted, and any geometry can have any statistic, figuring out novel combinations of the ways that those interact give us really cool plots. Okay? So that's one that I've seen some students use before, probably because I think I used it earlier. And that's just an example of the fact that a B swarm is a plot about points, and it tries to plot them using an identity function, but it also pushes them apart if they're too close to one another, if there are too many identities in the same location. So there's a separation between the actual geometry and the statistic that it uses. But by default, we generally just use the standard statistic that's packaged with the geometry. Okay? So each of these things are the modern way to express a mapping between a geometry and a statistic. So generally speaking, if you really need to, you can fiddle with the stuff under the hood. But geom_point is going to look like a collection of points at a particular location. Geom_histogram is going to try and count how many points fall in that histogram area. Geom_bswarm is going to do the same as a histogram, but try and get them very close to their original positions. The box plot is going to give you the familiar visualization we all love and can make a ton of, because box plots, I think, are the most useful visualization in exploratory analysis. And the geom bar is kind of like a histogram, except for it just is recording the position by the height of the bar. Okay, so all of these are graphical primitives. All of them are geometries that come with kind of a default statistic that records the position of your data. In the language of ggplot, we call these layers. All of this is a layer. Anytime you see a geom point, it's a layer. And the interesting thing is that for geographers, geom map, which is exposed by some packages like ggmap, traditional GIS software and the way of geographers thinking about the world are also functionally organized in layers. We make thematic maps by adding together base maps on top of boundary maps, maybe an additional choropleth layer. So this should be relatively easy for you to understand. Each of these things works as a layer to summarize the data. I'm going to move on from the theory of the layer and just talk a little bit about coordinate scales, guides, and axes. So as before, if I had my plot where I had my points from the publication, we talked about these being scales. So a scale is something that gives you an indication of the size of the values in the plot. So just controlling where they're plotted doesn't give us enough information about what they're, how they're plotted or the positions. So the two kind of main common scales that you see are the use of either two scales to present this kind of information, and we can use a linear scale where every point is kind of, actually I need to use this, where every unit is the same length. But then you can also plot on what's called a logarithmic scale. And in a logarithmic scale, each tick mark increases in an exponential fashion or decreases in an exponential fashion, depending on the direction you're traveling. So normally how this looks is that your tick marks become closer and closer together up to a point, and then they resume the same pattern of change up to a point, and then they start again. And we use logarithmic plotting when distributions are incredibly skewed. And you can independently specify a log on your x-axis, a log on your y-axis, or at the same time log on both axes. So anytime you've seen a GG parameter, that's scale, and then something else, that's referring to the visual scale. But the other thing that the scale primitives can do is talk about color. So only one of the kinds of visual variables that you're working with here are the labels that you put on your axes. It's also a scale if we're talking about how variables are colored. So if I'm using a color map and some observations are lighter than others, that is also considered a scale. So you might have seen like scale color discrete or color scale continuous, things like this. In ggplot, those are also considered to be scale components, and you can adjust them without adjusting anything else about the plot. That also means that cartographically, color is considered a scale in this logic. Okay, so scale is anything that kind of gives you an orientation or helps you interpret the size or position or magnitude of the things in your plot. And the very last thing that I'd like to talk about is sort of the individual coordinate systems, because this gets pretty cool. So one visualization that we've made before in our course is the climate curve for Bristol. So we started off in January, went to a summer peak, and then went down to the next winter trough, right? And this was maybe temperature in degrees C, and this was month. And this was what January, February, March, April, May, June, July, August, September, October, November, December. And we made this curve. I showed you how to make this plot using a geom line, right? This is a coordinate system which is fundamentally Cartesian. Is the term. And all that means is that I have one or more axes, here I've got two, that are arranged at right angles. This is a right angle. And I can describe locations as a function of an X position and a Y position. Sorry, I didn't realize I was using the highlighter. I'm going to rewrite that. I can describe positions uniquely as an X position and a Y position. Okay? So that's a Cartesian coordinate system. Now, another important kind of coordinate system is known as a polar coordinate system. I'm going to move this over a little bit. Oh, geez, I didn't get it all. The polar coordinate system takes the same points, let's say the original here, February, March, April, May, June, July, August, September, October, November, December. I know that that's not matching up exactly, but just go with me for a moment. The polar coordinate system encodes positions instead of as an X and Y as a radius and an angle, sometimes called theta. And I think you may have seen this before, maybe. So in a polar plot of this same data, I have a starting point and I have a axis for my radius. And one of the common ways to plot temperature data in this particular example, let's say that this is a degrees Celsius, and say, you know, that's 5 degrees, that's 10 degrees, that's 15, that's 20. Okay, but I'm not going to draw that right now because it gets a little cluttered. But imagine that you have these tick marks that tell you how many degrees Celsius you have. And let's say the average January temperature is, I don't know, about 10. Actually, let's say it's about here. Okay? So we start that off just by saying, okay, I'm going to encode one of the values in my data set to a position of degrees Celsius of its temperature, and then it's the first month. So I'm going to put it at 0, let's say. Then I might want to put the next month at its degrees Celsius, but instead of putting it at an angle of 0, I might put it at an angle theta 1. So I go to the February temperature, which in this example is slightly warmer. I go over to the February temperature, and then I go around a particular number of degrees. So in this case, maybe let's say the February temperature goes there. And likewise, to plot the March temperature, I find its location on the radius and go around to the March temperature. And so a plot like this would manifest the climate curve as something like an ellipse. Maybe where our summer temperatures over this way get very big, and our winter temperatures get very close to the pole. So in the polar representation, each of these is a degrees Celsius and an angle at which the point lies. So again, that is the angle and the radius. And so polar plots are really useful when you have cyclical data. When at some point you get back to where you started and you want the presentation to be continuous. Is the angle significant? Well, in this example, I have 12 months. So each of the angles is going to be 360 divided by 12. So this one is going to be whatever that value is. I'm not going to do that off the top of my head, right? So 30 degrees cracker surface. So that one's going to be 30 degrees. The next one's going to be 60 degrees. The next one's going to be 90 degrees. And so on and so forth as I walk around the circle on which I'm plotting these. So that's how polar coordinates work. You're going around in a circle and you're plotting out to a given magnitude. And you'll see some examples of these in the online example as well. It's not like a pie chart where the area reflects the data. It's like a position where things happen. So one possible example might be something like this, where, giving myself a little more room, say I'm visualizing the noise of a city in decibels at all of the times of the day. So let's say this angle here represents 3 a.m., like it's a clock. At every moment in time, as I go around the clock, I'm going to say at 3 a.m. it's very quiet. And then as it gets later in the morning, it gets louder. And then during the day, it gets really, really loud. And at noon, it's much louder than when we started. And then in the afternoon, it gets quieter throughout the afternoon. And then, so now this is 3 p.m. So it gets a little bit louder rush hour, and then it's going to go back down and get quieter at night. So how far away this gets from the center indicates how loud that time of day is. The angle represents the time of day, and the distance from our center reflects how loud it is. That's like a polar encoding. Your location is a combination of your angle and your distance from the center. And that's what makes it polar. Your location there of your geometry, the position, is a function of loudness, in this case your decibels, and your angle, which might tell us what time of day it is. Okay? So we're taking the cyclical data and we're mapping it back to the this other space. So that's a polar coordinate system. And these are oftentimes presented as the two different kinds of coordinate systems that are used in visualizations, and you'll see quite a few of them in the examples. Of course, you can have geographic coordinate systems, which can be both Cartesian and polar in their nature. Many of the things that you're aware of, like latitude and longitude, are polar coordinates. So in the Earth, if we think of the Earth as a sphere, your position in latitude and longitude is a measure of two angles. How high you have to go to get where you are, that's your latitude. And then how far from the meridian you have to go, and that's your longitude. The radius, we assume, is constant. So latitude and longitude generally are polar denominated quantities. They're three-dimensional, so you get radius, latitude, and longitude. And we just assume this is constant, and we talk about latitude and longitude. Okay? So I just wanted to talk a little bit about those systems, Cartesian and polar. And the very last bit that I want to talk about is the use of faceting. This is facet. A plot can be made up of a bunch of different components. As we see in the grammar of graphics, it contains many different layers, and it can contain different scales. But a plot can also be composed of many different subplots. So one way you can think about this is if I have two sort of plots, and I'm showing one country's climate curve in the northern hemisphere and one country's climate curve in the southern hemisphere. Each of these is a facet. So when you see a subplot, you can think about it as a facet. And normally, how this works is you use a function like facet grid that describes the unique data that falls within this plot. So in this example, I might say facet my grid by country. And then I would get unique plots for the climate curves of every country in my data set. Okay? I might also get a two-dimensional faceting. Where I might be talking about, say, I don't know, voted Trump, voted Biden. So we'll say voted Trump in 2016 and voted Biden in 2020. And then this one might be income. And then your internal Y might be something like, I don't know, let's make it simple. So income and, I don't know, number of kids. This plot would just describe the relationship between income and family size among people who voted for Trump in 2016, they're on the top here, and voted for Biden in 2020. This plot would only describe people that voted for Trump in 2016 and then voted for Trump again. So this principle of faceting breaks your plot out into different components. And this introduces a lot of additional complexities into plotting. For instance, are your coordinate systems aligned? If I have a position in this plot, is that the same as the position in this plot? Is the minimum x value, which might be 0 in this one, the same as the minimum x value, which might be 5 in that one? So these are the different aspects of kind of figure design that you need to be aware of when you're talking about faceting. But you need to know that faceting is the process of splitting your data and making what they call small multiples of visualizations. It's kind of like a group by. Exactly, Finn. A faceting is exactly like a visual group by. Each one gets split off and dealt with separately. So to close this, the main point is to break down the ggplot structure. And what I hope I've shown you is that you have ggplot on your data, and you're going to specify some aesthetic mapping on the x-axis and the y-axis with possibly other things like scale, color, fill, or whatever. You're going to add to that generic specification a geometry of some kind, which can have its own aesthetics and also its own data, but then also has a statistic that it uses implicitly to summarize your data. Then I might involve something like a scale, and then I might change it to polar, which would be chord, or I might keep it as Cartesian, which is the default, and then I can facet by a group or collection of groupings. Everything in ggplot is something in this category. Either you're faceting, you're changing the coordinate system, you're dealing with scales and guides, or you're dealing with the geometry. That's it. ggplot is a way to talk about the interactions between these components. And it's really cool because ggplot is the first majorly successful version of this kind of system. But it's kind of eaten the world. There are other systems beyond ggplot. You might be familiar with or have heard of a system called Vega in web design, which relies on the exact same principles that are explored in ggplot. Or there's also something like Altair, a clone of Vega, that do the same thing. So this idea of thinking about plotting in a structured way as layers that have scales, an implicit coordinate system,
and then that can be faceted or combined is completely ubiquitous. This is how people think about plotting now. And ggplot was the first real popular technical system that did this. Next week, I'll talk a little bit about how you go about telling a story with plots. But I wanted to give you this vocabulary so that we could get there. I need you to know that when we talk about a geometry, I'm referring to a pair of a shape and a statistic. I need you to know when we talk about rescaling the data that it's done by these kinds of scale constructs. I need you to know the difference between a coordinate plot and a polar plot, although I probably won't ask you to explain that in mathematics. I need you to recognize when you're looking at a coordinate plot, or a Cartesian plot versus a polar plot. And I'm going to need you to know how to facet. So each of these things are likely going to be on your assignment. So I need you to know what the geom means and how it works, and then a couple of the common geoms that we've talked about today. You're going to need to know how to rescale a graphic. I may ask you to change a graphic from Cartesian to polar, and I also may ask you to facet something and explain what happened. Okay, these are the primitives of ggplot. Now next week, there's a reading on this data from Viz. And that will be supremely helpful for you to understand the mappings between the geometries you want, the stats you want to show, and what they're called. And that's kind of really going to be the fun visual tour of all the different kinds of plots. But today, I just wanted to make sure you had the vocabulary to talk about this first. Okay? So that's the lecture for today.